Okay, welcome to the Wednesday of the second week. Today is the last lecture of Sasha. So please, Sasha, take it
Thank
over.
you. Yeah, one comment. So I mentioned some references and maybe formulas were sometimes messy. I will send the notes to Francesco, and I guess you can all download it somewhere, so in case you're interested. I would like to talk today next, as we discussed, about some stringy features of gravitational scattering, and then say a few words about black holes, and conclude where we stand. For stringy features, as we discussed, there are several scales to consider. First, if we assume that we have say some stringy completions, then of course we have a string scale, and the length of the string is 1 over ms, and we consider the string coupling to be very small. Then there is a Planck scale, which is given by ms divided by g string 2 over d minus 2. Then there is this correspondence point defined by Schwarzschild radius equal to string length, and this corresponds to, let me call it S star equal to ms over gs squared. This is already discussed. Finally, we will have some new emergent scale where stringy and elastic effects will become important. It will be at, let me call it stringy, which will come as ms divided by first power of g string. So this is the lightest scale, then comes M Planck, then comes string effects, then comes the correspondence point, and here things will, at the correspondence point, as usual, when we approach the Schwarzschild radius, things break down and perturbative control is lost. Finally, the basic two effects I would like to discuss is that there is tidal effects. This is and this we already talked about a little bit. And the basic point here is that already, even though you imagine that the string has some string length, already at impact parameter much larger than string length, you will have excitations of a string. And second, there is a, so if you want, this is a kind of a T-channel effect. And there will be S-channel production, or S-channel production of strings in the direct channel, and this happens as expected for B less or equal than ls square root log ls square s. So this is sometimes called transverse spreading of the string. So transverse spreading. And this is related to, oh, it's already wrote it, sorry. Now, to derive it, we need I will start with this. I will quickly review this, and this comes from, as usual, tree level, and this comes from some kind of stringy iconal. So let me review quickly what's the basic point. Let's do, say, correction to the phase shift, and basically what we want to do is to understand, let's say we can take the amplitude at tree level. We consider scattering of scalars, it would be dilatons, and to go to string theory, we start with the tree level amplitude, SUT. This is what we've been studied so far. This is just a tree level amplitude, and what happens in string theory, we dress it with a famous factor. Here, it's 1 minus prime s, gamma 1 minus prime t, gamma alpha prime u. And here we have gamma 1 plus alpha prime s. Gamma. And as usual, of course, s plus t plus u equal to 0. So this is a famous expression. Now, at low energies, we get the back what we discussed, but we are interested in the corrections at high energy. And the basic formula here is that if you take the radial limit, what you get is that, let's say we take s to be large, we get the following familiar formula. Is previous result that we have, s square over t, but now it is dressed by s to the alpha prime t, and here, I think I put here a factor of 2, and here we have gamma 1 minus t, gamma 1 plus t, and 2 minus prime t, and the phase. So this is just the radial limit of the previous formula, and now what we do, or what we want to understand, it's the string effects are in this phase. So this is all very standard. And what we do, we take this formula in the radial limit, and we look at it in the impact parameter space. So if you do the impact parameter transform, sorry? Oh, yeah. That's, okay. Yeah, thank you. Okay, let's do the Fourier transform, and you can do it. It's well. So what you do here is you take 1 over to s. You do the integral over the transverse momenta, if you remember, and then you plug this formula. Now, as you do that, you observe 2 basic effects that I would like to mention. First, you have an emergent scale. So let me introduce it. If I put this s into the exponent, it's natural to introduce this, let's say, call it y. It's log minus is over 2, something like this. So this is simply coming from taking this s into the exponent and combining it with this phase. And then things will be different. There are 2 regimes. When b is much larger than, let's say, y, and this y is nothing but, again, sorry, this is exactly this transverse spreading of the string. So we have this scale, which is enhanced by the logarithm. And so when you have b much larger than square root y, Maybe let me restore this alpha s square here and here so that it's clear. So when b is much larger than what you get the Ts of b is a tree-level result. Sorry, GR. You get what we got in GR. Plus, you have corrections. You have the interesting thing is that the amplitude develops non-trivial imaginary part, and the imaginary part is exponentially, so ignore the exact factor, but the important point here is that you have minus b squared divided by y. So basically, when b squared approaches y, you start producing, the amplitude start developing imaginary part, which is related to production of strings in the direct channel, and this is what we got before. So just the basic point is that when b approaches this logarithmically enhanced scale, we expect yeah, so you see that it's imaginary because y has this minus I. So if you expand that, you will see that it has an imaginary part. And the second regime is when b becomes much less than this square root y. The amplitude simply becomes follows. So you get square root y, d minus 4, and you have corrections which are organized as an expansion in b squared over y. So the basic point here is that effectively what you see, what happens, this looks like a tree-level phase shift in gravity, where instead of b, we have this emergent scale, and with just, as you try to decrease impact parameters, if you approach y, it looks like you're scattering object of finite size, and so then you just get the size of this object, which is y instead of b. And the punchline is that if you look at the phase shift as a function of impact parameter, you have the scale ls log alpha prime s. And if you look at the real part, it starts as a power 1 over it has this 1 over power bd minus 4, and then it just caps off to a constant, which is of order g Newton s. So this is just this formula where we're ignoring this log. So when b is small, it goes to g Newton s, and then at large impact parameter, it goes to this power. And this is the real part. And the imaginary part, it's exponentially damped, and it's like this. So this is the imaginary part of delta. So this is, if you wish, this is a correction to the our computation with just a tree-level graviton. We have these new effects. One is effectively, it's as if your object has finite size, as some beams of energy of effective size alpha prime log s, so it's small impact parameters. Everything is caps off at this size. And second, because you have this S-channel resonances at this scale, you start seeing that the phase shift develop imaginary part. Now, so this is a generalization of the simple tree-level computation. Now we can do the second part and consider the propagation through the shock wave.
Sorry, this 1 over b to the d minus 4 in the real part, where did it come from?
This one?
Yeah.
So this is, if you remember, In 3-level GR, we have this result.
That's just the GR part.
This is just the GR result. So we, as expected, we recover GR at large B, and this scales, the corrections kick in, and this grows, saturates, and
the imaginary part is exponentially suppressed.
And the imaginary part is exponentially suppressed. That's a basic picture of this computation.
Thank you.
This is you look at just the phase shift of the stringy phase shift, which is given by the Fourier transform of this Regge amplitude. So there are corrections which are suppressed. So here we take the correction to this correction to the Regge limit, so they're 1 over S suppressed. What I took is that I took the full formula, we took the Regge limit, and we Fourier transformed. This was done. And after you Fourier transform, I also called it the phase shift, so the phase shift is exactly the same thing. And now I'm plotting the Fourier transform of this Regge amplitude in the impact parameter space, and there are two basic regimes. That is what I plot here. So this is saturates plus corrections of order B square over Y. Here and here. Well, here it's opposite. This is a phase shift. We are doing 3-level. We are not exponentiating anything. We're just taking a 3-level amplitude and doing Fourier transform. So I call it a phase shift because when the phase shift is small, you just expand it and it becomes a 3-level computation. Now we will be exponentiating. But to exponentiate, we need to do a next step. Here we can go to really low energies, the phase shift is small, we don't have to exponentiate. So as you see, delta here is of order G Newton S, and this becomes of order, let's say 1 or whatever, when S is of order MS over G string. This was exactly the scale I mentioned at the first slide, is that when this guy becomes of order 1. For lower energies, this is very small. So yeah, when here G Newton is proportional to G string square, and so when S is MS over G string squared, you cancel G string and you get something order 1. And that's a first simple lesson. Is it clear? Yeah. Okay, so the question is, how does this picture compares to the other things we discussed, like black hole production and the gravity waves and etc. So remember, all these other scales grow with S like a power, and this grows like a log. So it is not there, but to go to this other mechanism, we need to consider higher energies, and to consider high energies, we need to consider further effects. Well, it will be. It depends on the energy, you know. So it's if you take the Schwarzschild radius. If we take a very weak coupling, the Schwarzschild radius is tiny. We never form any black holes. You know, because R Schwarzschild, let me remind you, R Schwarzschild d minus 3, it's give me a second. So this is R Schwarzschild, and so if you take this energy, say if you take G string to be very small, we always, in the regime R Schwarzschild, much less say, in general, so here I want to consider the stringy regime, so I will take R Schwarzschild to be much less than LS. But of course, this condition, it's a condition on energy, because LS, say, we can do here, this guy is G Newton square root s to the 1 d minus 3. This is this condition. So the answer to your question depends on the energy. As you increase the energy, Schwarzschild radius crosses all this picture. As you go to low energies, Schwarzschild radius does not play any role, and that's why we trust tree level. So depending on this picture, it makes sense, because we have if we have a tree level approximation when the Schwarzschild radius is very small or string coupling is very weak. So you can, but as we increase energy, our Schwarzschild grows, this picture doesn't change, and so then we have to reconsider. Yeah. So this is the first condition, and the second condition is S alpha prime much larger than 1. So this does not depend on G string, so you can go to the Regge limit of the tree level amplitude. This has G string in it, so you take G string to be very small. This is when they're equal, so if you wish, on the S plane, we had MS, we have MS over G string squared. This is the corresponding point. So this is RS equal to LS. So we are sitting somewhere here. M Planck is somewhere here. It's between these two, and when this guy becomes 1, it's when square root S is of order MS over G string. So sorry, let me do square root S. So here, this is MS over GS, and here is M Planck. So in particular, we will cross M Planck. We will go to energies higher than M Planck. This will be completely fine. We consider trans-Planckian scattering, but where things really go hard is here. So, but here we will be able to say something by equalizing. And here again, if we draw B, there is the scale LS log for prime S square root, and so when you're below the scale, all the string effects kick in. When you're above, you have small corrections. That's a basic picture. So far, here we now been doing, if we do tree level, we take MS to be large, but say the inelasticity is very small, so we can be somewhere above MS, but below this point, and then the tree level computation is fine. Next, if you remember, our step was we had this propagation through the shock wave. So let's consider string propagation through the shock wave. And it's a famous fact that if you consider this Exelburg-Sexel background and you consider just a string on this background, it is solvable. So you can solve the equations of motion for the string. Remember that let me just remind quickly what it was. The shockwave background was, if you remember, dx minus dx plus delta plus dx. Yeah. Please go. No, you don't have part. Well, you have part, but you have resonances in the S channel, right? So these resonances, they lead to imaginary part, and this is the imaginary part that we see. So the imaginary part of this delta, you interpret it as you just form these resonances in this. It's in effect, it's in effect, it's this usual story that you start with a bunch of poles, and then we go a little bit in the imaginary axis, and so this guy has an imaginary part, which is just an effect of these poles. Yeah. Black disk, it will all come later. So there is no black disk. I would say that eventually, yes. Eventually, what will happen is that if we go to higher energies, we can start producing not just one string, but many strings, and we can get tidal excitations, and all these things effectively, in the end, looks like some kind of black disk. Please.
Since you're just doing tree-level, I would have thought that the condition is that the loop correction is small.
Yeah.
So in the diagram that you wrote earlier,
Yeah.
Long before you get to the correspondence point, you will have to take into account loop corrections.
Yes, exactly. Yes. So that's what we will. That's what this iconization does. But then, if you're sitting in the regime where the energy is large and the effective exchange in the T channel is small, the idea is that we can control these loop corrections, like we did it with the shockwave propagation.
Okay, so that's will be the equalization. But at this stage, you haven't done that, so you're still in
This is just a tree-level computation. Yes, I haven't done that, and effectively there will be two effects. One is simpler. One is a bit more complicated and I guess less controlled. The simple one is that you have this, let me remind you, we had this shockwave geometry where we have some energetic particle, which plus transverse. And now we want to propagate a string through this shockwave background, and the statement is that it is you can solve the string equation of motions. It was done first at the 80s, and the result is very simple. What you get is the same S matrix that we had before. So you write worldsheet coordinate in a light cone gauge, and then you solve the equations, and you find that if you have a string propagating on a shockwave, the result is simply as before, you exponentiate this phase shift, and you get something which looks like 4g Newton S. But instead of this this type of simple factor, you have the worldsheet integral, and this guy becomes an operator which acts on a string Hilbert space, and here you have this transverse x on the worldsheet evaluated at say 0 worldsheet time and sigma minus to the power d minus 4. So the basic point is that now you write this x as a center of mass little x plus stringy oscillators. And you have now, if you want to propagate through the shockwave, in principle, you can start expanding this x around some large x. There will be stringy oscillator corrections. And when you evaluate, say, if you consider your S hat is you solve the equations of motion for the probe string on this background. You send a string, it propagates through the shock, something comes out. So you solve just the classical stringy solutions of equations of motions, and the statement is that S shock is a S matrix for the string propagation in this background. It's a solvable. It's the analog of at large B. It's an operator which acts on a one string Hilbert space. It's an operator which acts on a one Hilbert space and which is an operator of a string propagating through the shock wave. So if you send this, you take a string prepared in some state, you send it through the shock wave, this is what you get. You act with this S shock on the, say, your string states, and this is your outgoing state. So it's an S matrix. It's an S matrix, but it's in the one string states. In other words, let's say we write a wall sheet, equations of motion on this background, and you can solve them exactly. Before and after shock wave, it's a free theory. Now you have a junction at the position of the shock wave, and this is a junction which maps it to some kind of Bogoliubov transformation.
I'm not sure I get the notation, so let me understand. So
Yeah.
I send an int string with some parameterized by some oscillators.
Yes, so
And I
let's
get
say you
some out
prepare psi in, and after you propagate through the shock wave, this is your state for psi out. So in particular, if you want to consider elastic amplitude,
Right.
you evaluate.
So where in your formula do I see in and out data? I only saw there was only X. And X is some
X is an
oscillator.
operator, right? X is operator, which is a string, is a wall sheet operator, which has the usual expansion in terms of the string oscillators.
Ah, okay.
So this is operator. It has a center of mass, and so at large impact parameters, the contribution of the stringy oscillators is small.
Oh, I see.
And but then you can expand it to first order, and
Looks very impressive, this formula. How was it?
well, this
computed?
is I think it's a formula from 1987 or something. It's this fact about this shock waves that they're simple enough that you can solve it. But this formula is not yet good enough, because you can ask what are the corrections to this formula, and I think the answer is that this formula misses corrections which are in a physical process. We don't want to consider the shock wave, but we want to consider the second string, right, effectively. And so this would be the next step. But I just wanted to show you because it's such a simple example. And
Can you just give a basic idea? I mean,
yeah,
mathematically, how did this power d-4 and 1 over
Yeah.
an oscillator? What
It's-
was
it's-
going on? What was the technique used to get to such thing?
So this you start with the solutions to the GR equations with some source, which is this. This is what we did last time. And now we can see the string equations of motion on this background. And the basic thing is that it's free before and it's free after, and then you have to match. And so this is like we solved the wave equation, and that's what was the effect. Here the statement is that you just do it on the wall sheet, and this is the effect. So the string oscillators get excited, and you can compute this effect. Yes, the B in the matrix is transverse. This is the position of center of mass. So okay, you can choose this B, yes, and then you can send yeah. It's just this transverse X. So it's the same matrix that we considered in the first lecture. It's just we're now not doing a free particle, we're doing free string on this background. Yeah.
I didn't understand. What is the correction you're referring to? I mean, isn't this background exact?
It's an exact background, but let me do a next step, and then I will compare to this background and ask what does it capture. Because I think then this is an exact background, but if we are interested in a 2-2-2 scattering of gravitons, we can ask, is this background relevant or not, and what does it capture? This is a correction, yeah, I meant. So that's a very simple exercise that one can do. And then you evaluate this element in this, say, in a stringy vacuum. And this you can do. Well, there is an exact formula, but basically what you get as expected, is that at large impact parameters, you get some formula, as we discussed in our first lecture, which is you have this tidal effects, which scale is 1 over bd minus 2. So in other words, there is a scale, which is this b tidal, where remember we discussed if you consider collisions of two shock waves, when the curvature scalar becomes of the string scale, we expect that string gets excited, and this is precisely this expression which you can confirm by an explicit computation. So in other words, when this guy becomes say order 1, you expect to have large tidal excitations. Now, one way you can improve, you can try to ask, can we improve that? And well, there is one obvious thing, is that we should treat both strings on the same footing. So here we consider some background, but what if we consider the strings on the same footing? And this is this formula, famous formula.
Sorry, Sasha.
Yeah.
So why do we get the tidal effects from the shock wave, but previously we got this iconalized amplitude from the shock wave?
Yeah, so this is iconalized amplitude, right? Because it has a phase shift.
Yeah.
But on top of this, it's not just an amplitude. We got an operator, which is a unitary operator in a one-string Hilbert space. And now it involves transition where a string gets excited. But if you project it, you get the. Sorry, I think that's what you referred to probably.
Ah.
Sorry, thank you. Yes,
Yeah.
there is everything we said before is there, but now as you go, if you take the absolute value, you start getting this stringy effects. So the next to connect to this problem of this was very simple background to solve. Yeah.
Sorry, it's very basic. So you had these lines before in the one lecture ago, right? Where we're in the BS plane, and what we are doing now is we started the leftmost one and we went down. That was the first part of the lecture, right? And now we are going to.
Yeah. So now
there were some gravity waves and tidal. Which one was first?
So there was
This was
tree.
Reggie, right?
There was iconal, and then there was tidal.
Ah, okay. And gravity waves is the next one.
The gravity waves is there. Yeah. So
Okay.
gravity waves is next.
Okay. It depended on dimension, right? Which one was first?
Yeah. That's dependent on dimension. So here I'm,
Okay.
I'm
I see.
doing.
I see. So, and the previous exercise we just did was this 3.
Yeah, it was just
We
3.
did
It was
And
just
now
3.
we are doing tidal.
And
Okay.
now, and there was this corner when B becomes of order ls log.
And in the previous part right now, we learned about the vicinity of the dashed line, right?
Exactly.
We cannot
yeah.
go down too much, otherwise higher loops and so on kick in, like Leonardo was saying, right? In B.
Yes.
Okay.
Okay. Now let me. This is a simple exercise. A more complicated exercise is to do the analog of this iconal diagrams in string theory, and this is what the main result of ACV, which they say that there is a unitary S matrix which acts on the space of two strings, which is takes the following form. You take e to the I, and now you have two strings that gets scattered, and here you have this operator, we call it tree, which depends on S, and now depends on this operators of the upper string, say minus operators of the lower string. So this is this delta tree is remember what was say in GR it was just this x up minus x down was a d minus 4, and then when we went to small impact parameters, we had the correction due to the excitation of the oscillators. So that's a basic result, and the sort of nice thing about this result, it's not just some amplitude. To evaluate the amplitude, you do this, but it's really a unitary operator in a space of two string states. If you compare the difference between this result and the shock wave, well, they are more or less the same as far as this sort of formula concerns. The only difference is that now we treat both strings on the same footing. It's very natural from this point of view. We simply treat both strings in the same way, and in particular, the tidal excitations of this operator are the same. But there is a second effect, which is, remember that when we considered this tree-level scattering, there were corrections due to other effects, such as a production in the S channels. There are S resonances, and in principle, you can include that. So this delta tree, if we take it, the one derived from tree-level amplitude, it stops being real. And you can ask, what is then the interpretation of this formula if this operator stops, if it stops being real? And there is a formal way to, basically, the physical picture is that you start producing strings in the S channel, so you have to extend your Hilbert space. You cannot have it, I think it's the old version now. If you turn on the imaginary part of delta tree to be non-zero, then it stops. It's not a Hermitian operator anymore. An interpretation of this is simply that you have to include the states, more string states produced in an S channel. And in fact, there is a simple formula you can write where you introduce an effective Hilbert space of kind of S channel, what people call gravi regions, but effectively increases your Hilbert space. And you can rewrite this operator, well, where delta tree is what we did in the first part. It's a Fourier transform of a Regge limit of a tree-level amplitude. And this operator becomes a unitary operator in this extended Hilbert space, which supposed to signify this production of S channel strings. So yeah.
It's on.
Just to understand, so in terms of diagrams, these would be like ladders of like strings at the top, strings at the bottom.
So in terms of diagrams, well, you take just the string loops, and then the idea is that we are sitting in the regime where the momentum transfer, the energy is big, and the momentum transfer is small. So therefore, you can effectively, you start gluing these tree-level regions exchanges that we did in the first part. And when you glue these region exchanges, that's what they did. You get this S matrix. So in particular, if your energy, whenever the energy drops down or the T-channel exchange becomes big, so that this approximation of an amplitude by the Regge limit does not make sense, this formula is supposed to break down. But basically, it's the same as a iconal in string theory.
So you're basically iconalizing the Veneziano tree-level amplitude, or sorry?
Kind of, yes. It's a tree-level. It's iconalization in the impact parameter space.
Yeah.
Where these guys are now operators. It's not numbers, but these are operators which act on a Hilbert space. And then these are the two main effects. So yes, the two main effects is first the tidal excitations, which kick in at LS much larger than at B, at impact parameters much larger than LS. And the second effect, is which you go here, you expect the amplitude to become inelastic. And in fact, if you continue this line of tidal and you evaluate it at these impact parameters, the inelastic effect due to tidal effects and the inelastic effect due to this imaginary delta, they exactly match. And so from this point of view, you expect that, say, in this region, the amplitude becomes inelastic and becomes of order what you expect from tidal, but evaluated on this effective scale y at d minus 2 over 2. So this is a sort of expectation. If you have these tidal excitations, then when you go to small impact parameters, you have this region where the amplitude is effectively controlled instead of impact parameter by this scale y, which is related to this transverse spreading of the string. And then another interesting fact is that when you evaluate this at the correspondence point, so let me do square root s, g string square, then this, if you evaluate it here, it matches to the black hole entropy, roughly, if ignoring the logs. So you get roughly, again, some e to the minus s black hole. So that's the basic picture, that what happens is effectively we substitute b with this scale, but then, again, things become very, very inelastic. Now, let me, yeah.
So these tidal effects, they are like production in the S channel of excitation of these modes. But is it also included excitation of the T channel exchanges, like the kind of?
No, here this formula, this ACV formula only makes sense when you exchange in when we really whenever this Regge approximation to the amplitude makes sense. So, which I think yeah, so what this ACV formula does, it effectively resums the amplitudes where we approximate the exchanges by this region exchange. Now, in some sense, this formula does have the excitations in the T channel, but notice that we are sitting in the physical kinematic, so T is negative.
Yeah, but in impact parameter space, you could see an effect of this tidal excitation. But I guess it would be like Yukawa, like suppressed.
So you see exactly this. This is the effect of these guys. This is there is no, because there are infinitely many of them, you don't have Yukawa, but you have B square over Y. And this is exactly the effect of these guys.
Right, yeah.
So now I want to make few more comments.
Is it possible to draw some pictures? You are mentioning several times S channel, T channel, and so on. I'm having a hard time visualizing where are the multiparticles.
Yes. No, I definitely. So let's say we have a scattering of strings. So the ACV formula, its basic content is that each piece of the string interacts with each piece of the string here. So this is XU, this is XD. And so we have this operator where when I wrote the ACV operator, well, like this one, this is not the ACV, so let me go to ACV. Yeah, this one, so this is XU and this is XD. This is a point on the upper and lower string. So we have this, this is what I call the T channel. So this corresponds to the exchange of this region in this channel. The S channel is this, and the idea here is that the effective size of the strings that we can exchange grows with S, so it's of the size ls square root log s alpha prime, and so then when the strings become close enough at this order, they effectively the production in the S channel becomes efficient. That's a picture. So when impact parameters are large, this effect is absent. When it becomes smaller, it becomes important. That's
so this is exponentiated. So there would be many T exchanges, right? So
Yeah,
if I
yeah,
cut in the T channel, I see many particles. But if I cut in the S channel naively, I see 2 cylinders only. So where is the particle production in the S channel?
Yeah. So the effect, the way it comes about is that you see that this operator, when the imaginary part, this is a bit confusing. It's a bit confusing, I find myself, but I can tell you what's done. What's done is that, so this is a Hermitian operator when this guy is real. Imagine you add here something like this, I minus b square log y. So now this is something which is not an S matrix operator in this 2-particle Hilbert space because it's not unitary, but you can still compute the amplitudes. The claim is what you can do is that you introduce an extra bosonic oscillator, CC dagger, which creates this kind of region collective excitation in the S channel. So we see it on some resonances. In principle, we should be discussing all kinds of multi-particle string states, but there is just a very concrete technical claim, which is that if you take this operator and you take the tree-level guy that has an imaginary part, you can write it as a unitary operator, but now you extend your Hilbert space to include these multi-particle states of C, which you interpret as this effective gravity region states in the S channel. This is a sharp statement. So there is a unitary operator in an extended Hilbert space, which takes care of these excitations. Now, what exactly it's supposed to mean? I guess the picture is that it's supposed to capture some coarse-grained version of production of strings in the S channel, but at the technical level, it simply takes care of this. It's a unitary operator which takes care of these imaginary parts. In other words, you extend your Hilbert space, you introduce the C daggers, you write a unitary operator, but now you evaluated this S matrix in a vacuum, and it just boils down to this with the imaginary part. So it's equivalent.
So, sorry, Sasha. Maybe in the cylinder picture, I don't know if where's the slide?
The confusion may be coming from the fact that you drew this X line connecting XU and XD as purely transverse, but in fact, it has some longitudinal component, and so you can actually cut this line.
Yes. So
and there are going to be many of these lines. They're going to be crossing in different ways. So you can make maybe more.
I can make it
picture.
fat. Yeah, I can make it fat, but it's analogous to the fact that this guy develops an imaginary part in S channel. So which we interpret as a production in S channel, so you can cut it. So this amplitude, when we go and look at the imaginary part, if we cut it, it effectively measures the production of resonances in the S channel. And so when we exponentiated this guy, effectively we also can cut it, but now we do not write all these resonances one by one, but we can say, okay, the collective effect should be something of this type. And the precise technical statement is that you can simply rewrite this ACV operator as a unitary operator in the extended Hilbert space, which has these gravity regions.
But can I ask a question?
Yeah.
So at this level of accuracy, isn't this just a graviton state? Because it seems to me, since you have this 1 over x to the d minus 4
this is just a graviton. So all this is irrelevant when the imaginary part of delta is small. It only becomes relevant when you go to impact parameters small enough to produce this kind of effects. So here it's all irrelevant, but it becomes relevant becomes relevant here.
So would it be incorrect to say that these are just some gravitons? This what you call regions.
We can call the regiized gravitons. So this is a graviton, because graviton itself would not produce any imaginary part, but when we attach a regio trajectory to it, then yes.
But this regiization, okay, it's important when you consider the T-channel exchange, but when you talk about some produced particles in the S-channel,
yeah.
I mean, what can this be? I mean, wouldn't this be just
this
gravitational waves? No?
Well, the S is big, so this would be some stringy
States.
states. This is some stringy states, right? In the S channel, S is big, and we see it alpha prime S is much larger than 1.
Okay.
So these are really some...
So it's more complicated.
It's more complicated, yeah, it's a stringy effect. Exactly. Yes. Yeah.
So they are still gravitons, but in a region which is in the vicinity of many, many resonances, so their behavior changes a little bit.
Yeah, that's I think the picture. But let me comment on few more effects.
Sorry, Sasha, can I just ask
Yeah.
So this naive question of this naive picture of the cylinder. So in the shockwave picture, you replace one cylinder by a line, right? Is one massless guy.
Yes.
So in that case, the S matrix basically connects one excited state of a string to another excited state, right? So that would be the production. Would be like an excitation of the string. That would be the diagram. That would give an imaginary part. Is that the naive? Is that the correct picture? So the production of particles, is it another mode of the string getting excited? That's it, or no?
So there are two things. So you can excite strings. So the tidal effect is really in a two-string Hilbert space, but a natural way to interpret this exponential, the imaginary part of the exponential thing, is just a production of strings. So it's a way. If you wish, you have to extend your Hilbert space, and this Hilbert space you cannot describe it fully, but roughly it should correspond to the fact that you start producing strings. I mean, it makes sense. You scatter things at high energies, at small impact parameters, you start producing strings. So.
Just to make it very clear, in the picture, in the slide with the cylinder, if you go back to it.
Yeah.
So on the left, I could have one state. On the right is a different state.
Yeah. You can excite this. You can excite this state. Yeah. Exactly. That's exactly right. So I wanted to comment quickly on a few aspects. One is behavior at fixed angles. So to do the fixed angles, if you remember, what we do is that we consider now amplitude at fixed S and T, and we do Fourier transform, and the exchange momentum is controlled by a saddle point. And before we studied this saddle point for the tree-level scattering, and so you can study this saddle point for in this regime of stringy scattering, and what you find is that it looks like this. So you have your angle. So this is our previous saddle point. Sorry, this is not angle. This is the angle. This is B. So this is what we discussed before. When you take a very small angle, that's corresponded to large impact parameters. So what happens is that if you consider this ACV operator, you have this real saddle point that dominates, which is here, which is this ACV saddle. But then you lose the saddle at some maximum angle. And the maximum angle is precisely, again, it's the same game. You take the ACV saddle and you substitute it by this transverse spreading of the string scale. So remember in the ACV subtle it was the same formula, but instead of this it was a B. And the amplitude, if you evaluate it on this ACV subtle, behaves, again, and this is the imaginary part, is due to the tidal effects. It is something e to the minus square root s, 1 minus 1 d minus 3 times some theta d minus 2 over d minus 3. So this is what we did is that we just take this amplitude now and we do the Fourier transform to evaluate it in impact parameter space in the real momentum, and you find that it is exponentially decaying on this ACV subtle. And what happens above this, the claim is that here you lose the real subtle and you develop a complex subtle. And if you evaluate your amplitude for theta larger than this maximal guy, you have a complex subtle. And this is what roughly matches to the Gross-Mende and Arguri formula. So you get the T is of order e to the minus square root s log s type of thing. So according to ACV, the picture is the following, that when you scatter at high energies but small angle, again, first, if you scatter really at high energies, it's all dominated by gravitational physics. That's what we discussed before. When you go to this stringy regime, when the energy is not too high, and you do scattering at small angles, you have some real saddle, which is decays slower than Gross-Mende. So this is a leading behavior, but then it's above some angles. The physical picture is that then you roughly matches to the Gross-Mende-Arguri saddle, which is supposed to control amplitude in this intermediate regime. Now, what is a precise matching, and if it's really true or if it makes sense, I would not be able to tell, but I'm just telling you what the picture is. The connection to Gross-Mende is supposed to be in this regime, and there you indeed reproduce the same behavior, and it corresponds to a complex saddle. And the second thing you find in this analysis is that the square root of s, yes, you don't remember square root of s. If you do Gross-Mende at tree level, you get s. But the whole point of the mystery of this is if you do Borel resummation, you get square root s log s, like in Serulus-Merton bound. And then the question was, okay, well, I don't know. Well, I mean, they do Borel summation of their saddles, all genus, and then they get something, and this something. Yeah, they famously find that as you go to high energies, the high genus on the saddle are less suppressed, so you have to resum. And then when you resum, you get something which is less, and that's what they got. And then one question in the subject is always, where is it, how does it agree with ACV, or where does it go? And the claim is that it roughly agrees with ACV in the region of this complex saddle, which corresponds to angles larger than this critical string angle. And the second point is that when you look at the position of the saddle, which is a now complex saddle in a B space, you find that for any angle, so you see that the position of this guy is as usual. It's always the same, ls square root log s alpha prime. So here it's a real saddle, and then also you get complex saddle. And so then what you find is that B is always larger than alpha prime than ls log alpha prime s. So you never probe, when you compute, naively you would like to probe maybe short distance physics, you do this high energy scattering at fixed angles, but you find that you never probe the B of the saddle is always larger than this, and this is what Veneziano calls generalized uncertainty principle. Because the basic picture is that we have delta x is larger or equals than 1 over delta p. This is the usual uncertainty principle, but then here you find that you can never go to delta x less than the string scale. So he writes it like this. So roughly, no matter how big is your p, you'll never be able to probe x less than alpha prime. But the precise statement is that if you do this tree-level computation, your saddle point and the impact parameter space is always like this. So that's a comment I wanted to make. Another comment next, which I wanted to briefly discuss, is a question about graviton pole. Last time we did this exercise where we reproduce a graviton pole through dispersion relations, but you know that if you take a string amplitude and you look at its discontinuity, it looks like something like this: G Newton, alpha prime, S alpha prime 2 minus alpha prime Q squared. And this was Slava's question, if you plug this formula into the integral of the type ds over s prime cube, s naught infinity, it correctly reproduces the expected pole. So it looks like the tree-level amplitude also can reproduce the pole, whereas last time I told you I reproduced it from the iconal. So what is the relationship between these two mechanisms? And the relationship is very simple. You plug here, if you look at this integral, you see that the saddle is located, so the energies that dominate in this integral, if you plug this amplitude, are of this form, 1 over alpha prime, e to the 1 alpha prime t. And I told you that in gravity there is this dimensionless quantity which controls transition when the gravitational corrections become important, and you can trust tree level when this is small. And if you evaluate this integral with this S star, which if you use the tree level and you impose this condition, you find that this is a good approximation when alpha prime t is, say, could be much less than 1, because we're interested in the pole, but it has to be much larger than 1 over log 1 over g string squared. So in other words, the idea is that if you have a string theory at weak coupling and you try to reproduce the pole using dispersion relations, in this intermediate range of t's, you can use the tree-level amplitude, but this t going to 0 serves to you effectively as a collider. When you send t to 0, you press the energies in this integral to be higher energies. Effectively, at finite m Planck, you cannot keep tree level. And so then, so this is, here you reproduce 1 over t from tree. But if you send t to 0, effectively you go to this iconal computation we did last time. So basically there is an effective scale in t which controls for you the transition from tree level to iconal. And of course, if you formally take G string to 0, it goes all the way to 0. So this is one comment about the graviton pole. So next, I also wanted to make, because I'm out of time, I wanted to make a comment about I'll just say in words. So you can also, okay, let me just finish with strings then. I just want to, can I have 5 minutes? I want to finish with the last computation because, so we discussed the string effects. I want to do one computation which has really black holes, and then finish with the last picture of the plane of S and J, and summarize. Maybe can I take a few more minutes? Sorry. I will try to wrap up as fast as possible. So first, the black holes, we see that we approach this picture, when we looked at this picture, and we seem to be seeing that as we approach this region from this or from this, we always get e to the minus s of black hole, and this is what is known. I think, as far as I know, this was mentioned by many people, but there is, at least in detail, it was discussed by Giddings and Srednitsky. They call it a black hole ansatz, which is just saying that this is the correct statement, that if you take the partial wave at high energies, they of order e to the minus s black hole when J is less or equals than J star of the collapse. Okay, so this is just promoting our vague observations into this conjecture. But this is a bit hard to justify, because this is something very small, and how do we know that it's small? But there is one computation which is kind of neat, which is the following. Imagine we are saying that black holes are supposed to violate all symmetries, so we should be able to compute what is the size of this effect. So can we compute it? For example, let's say we want to understand what is the lifetime of hydrogen to decay into two photons, or proton decay. And it's not, the process is zero in the standard model, and let's say we assume the UV completion in which it's only allowed for black holes. Can we estimate what is the size of the process? And let me simplify this situation where I imagine 4 free scalars coupled to GR minimally, and I look at the amplitudes, 1, 2, going to 3, 4. And if you have 4 free scalars minimally coupled to GR, this is 0 to all orders in G Newton. So it only can go non-perturbatively. So can we estimate this amplitude using black holes? Okay, so let me take imaginary part of Fj and write it using unitarity as 1, 2 going to some n times n going to 3, 4. This is just a unitarity relation for this process. Now, we expect that in such a theory, or in a UV completion where the only intermediate states are black holes, we say these words that, okay, well, let's then approximate this intermediate Hilbert space as this intermediate states as a state of a black hole. So then we get the formula im Fj 1, 2, 3, 4 equal to sum I to e to the s of a black hole, 1, 2, I, 3, 4. So this is a step. And then we say, well, first of all, if we collide 1 and 2 at a very small impact parameter, they form a black hole with probability 1. So this sum, if we take this sum, it should be roughly 1, which is to say that the probability to form a black hole in a high energy collision is roughly 1. But this matrix element is chaotic. It has some chaotic phase. So it's roughly then S black hole over 2 times a random phase. So then, clearly, if you take an absolute value, e to the minus s black hole over 2, this sum is correct. But now you plug this formula here. You have e to the minus s black hole. You sum over e to the s black hole. But you have random phases. So you get e to the minus s black hole over 2. Now, we want to compute something like this. So we want to evaluate the Wilson coefficient, say at low energies. So we can write dispersion relations for this amplitude, and we get the integral of, say, ds prime from the lightest black hole to infinity. And here we plug this e to the minus s black hole over 2, which is the imaginary part of f in the dispersion relation, imaginary part of the amplitude. And so we get the estimate that this is e to the minus s black hole of the lightest possible black hole over 2. This is a crude estimate, but I think this is the expectation in all this reasoning, that all the symmetries are broken. All the symmetries are broken by at least e to the minus s of the lightest black hole, which is, I think, completely phenomenologically irrelevant, which is a bit disappointing. But that's what it is. And just one comment is that this estimate, this was a rough computation, but there was a better computation done by Cheng, Maldacena, and Ba using these wormholes with the same conclusion. So and their computation required many technical details, which are quite precise, to make sure that it works. So, and their computation was, here it was, the key point about this computation is that we started with a setup where there are no other effects. So compared to black hole ansatz, there are all these other effects are present, and the idea is that it's still small. Here it's a bit simpler because we choose a setup where other effects are presumably there, and then indeed the small effects could be leading. But again, it's not clear if there is any UV complete theory of gravity where this calculation is relevant. So let me just finish with a final picture of what we're observing. So I will draw J and S. So, yeah. Yes, so exactly. It's supposed to be very small, but in the regime where we trust it, so let me put it here. So let's say we have MS. So here we have low energies and any spins. And so here we think this is the EFT region. This is where people usually do various dispersion relations, and so this is EFT. So then we put here the correspondence point. Let me put square root S. MS over G string square. And here we believe this, well, there is this collapse. I don't know what it is. So here we have this region. It takes a while to paint it. So this is a collapse region. Oh, thank you. Oh, okay, anyhow. It just looks nice when it's really filled. So it's collapse. The scattering is supposed to be here chaotic with this random phases. And it's a black disk, so the amplitudes are very small and potentially e to the minus black hole over, say, 2. This is the partial waves, and this would be the size of the lightest black hole. Now here we have this other scale, and where we believe the ACV is controlled. So let's say there is some picture around this corresponding point where maybe there is some further insight possible. So we have this string black hole transition. Then, well, in J there is this, of course, there is this impact parameters. So this is Schwarzschild radius, so it's always overtakes. And this is the B of order LS. So here we have this ACV analysis. which is a stringy gravity. Here we have, okay, let me try this one. So this is iconal. Here things are, so this is a chaotic black disk. S is of roughly 0. The absolute value of S is roughly 0. Here S is 1. It's all simple. And here, then we have something which is less universal, non-universal, and sorry? Yes, I will not. So there is tidal, and then gravity waves. And the real question is, well, or something maybe which is a bit, could be a bit frustrating, is that, well, many people in this audience were very successful in doing Bootstrap, deriving some sharp bounds, in doing this twice subtracted dispersion relation or primal Bootstrap. And now you have this picture, and the question is it good for anything? Is it like helpful to improve any of the things we are doing? Is it sharp enough? What exactly we're supposed to do with this picture? It seems like there are basically two interesting things that this picture is telling us. First, there are many regions, both here, here, and here, where the scattering is effectively black. The inelasticity is very big. All S is larger, is order 0, and it seems in the S matrix Bootstrap we have a very poor understanding of this black disk-like S matrices. And so in general, if we can understand what is the maximal size of black disk, let's say we want to push this black hole region as far as possible. We want to S to be very small. Is there any systematic way or any way to use S matrix Bootstrap to bound black disks? And so far, the games we played seems to produce elastic amplitudes, mostly. So maybe there is something interesting there. And well, and the second effect is that there is very simple sort of integrable region, which is iconal, which we are supposed probably to also be able to understand. And then, of course, there are all kinds of detailed questions, but it seems like these are the basic two. The first, there is a very black disk region, and the question is, what is the size of black disk that is consistent with basic principles, and can we probe these factors, how small we can make it? And the second is that there is this iconal region which seems to be also controlling Reggie, and it would be nice to put it in. Sorry.
We had some toy model in our last paper with Andrea and John precisely where we did that. If the black disk was too big, then some rules that confused.
I see.
There was some coefficients would be violated, so we could put a bound
on the size of black disk.
So that
I see.
violate the known EFT things that
Okay. Cool.
But this transition, where does this region end, is always a bit murky.
Yes. Yeah. I think, yeah. I think that what they, I'm not sure exactly what the check will look like, because they, maybe it's maybe at one loop one can try to check if what they say about the Reggie limit of the amplitude is correct. Actually, I'm not sure. Maybe at one loop it has been done explicitly by Lawrence and Sebastian. At least when I talked to Lawrence and Sebastian and asked them, whatever you did, is it consistent with ACV? The answer was yes. So it seems to me that it is just a stringy iconal, and at least in this regime, it's pretty clear. Now, when you start having both S channel and T channel, this becomes a bit murky. But somehow this part of this stringy iconal here seems to be pretty clear because it's all very high impact parameters and says. But yes, this I agree. It's a bit murky.
Is there anything in this framework you could consider as being Hawking radiation?
So this is some speculation, which I don't understand very well. But the basic idea is that as you approach here, if you look at this ACV S matrix, which is unitary, and now you introduce this gravi regions, which is supposed to produce S multi-string states. So this is dagger C, guys. You can compute, you can estimate the number of strings produced and their energy in this region as you approach transition point. And it is not under well control, but with some conjectures, at least Gabriele claims to see that he sees the spectrum which sort of starts looking like you're producing many strings of the Hawking-like temperature. So that's the part I know, but this always, approaching this region is the trickiest and hard to control. But I think the answer is supposed to be yes, that you see something as you approach this corresponding point from this, which looks like Hawking radiation. Yeah.
Hello. I have a question. This region, this collapse region, it should be mapped to the phase space of a curved black hole, right?
Yeah.
Is this line then the extremality condition for the black hole?
Well, this line supposed to be the line if I scatter two particles at some impact parameter, when is the trapped surface formed? So
yeah, but does it match then J equals to M squared?
I think in the cases where I know it was done, it is some fraction of the Schwarzschild radius. I don't know if there is some detailed enough, because it's not the Kerr. You have two particles, you form, and then you radiate. It eventually becomes Kerr, but roughly it matches at least the Schwarzschild radius estimate. I don't know if there is a more detailed estimate. I mean, there are some, for example, when people write this black hole ansatz, they do put here the Kerr black hole entropy, but I don't know what's a justification for that. Maybe in this, if one does this Maldacena Chang-Ba calculation somehow at non-zero spin, maybe there one can see something more specific. But.
All right, thank you.
Sorry, can I ask a question about the toy model of 1, 2, go to 3, 4?
Yeah.
So we got a very small effect, right?
Yeah.
So, but then I was a bit worried that 1, 2 are not really particles with gravity, right? They are resonances. So already defining an amplitude is a bit subtle because they would not be asymptotic particles. But you would say, okay, but I don't care. They are almost perfect particles. The effect is the error is exponentially small. But then the result is exponentially small. So then I don't trust anything.
Yeah, you can take it like that. There are many more, much less conservative arguments where you start doing even more crazy things. But I thought at least I want just to give this example because people like to bring this up now. You might think, yes, that maybe it's, yeah, well, you made a legitimate point. So also this step of going from this N to some Hilbert space, you can say, okay, I'm not sure. It seems like a reasonable picture.
There are no more questions. Let's thank Sasha again for this wonderful lecture.
But I think if you take, say, electron, proton going to 2 photons, this should apply.
But then there is other forces. Then you cannot argue that they are.
No, but electron, okay.
We will come back at 12.